All right, how about now? Does that work? All right, perfect. Okay, problem solved. Well, let's get started here on carboxylic acids and carboxylic acid derivatives. Quite an interesting chapter, and there's a lot to cover here, so let's get started right away. And the first thing we'll cover is a functional group, right? And everybody by now knows what a carboxylic acid looks like. The general form of a carboxylic acid is shown right here. But when we put a generic R group like this, we assume that that's aliphatic. And if you're like, what does aliphatic mean? It just simply means not aromatic. Okay, so it's not an aromatic ring. And there we go. So that's a carboxyl group, and that gives us a carboxylic acid. And if we have an aromatic group, we can write AR like this to represent an aromatic ring. And so aromatic, of course, is a six-membered ring with alternating double and single bonds like that. And so we would have an aromatic carboxylic acid. And also in this chapter, I promised that not only do we discuss carboxylic acids, but we also discuss their derivatives. And esters are derivatives of carboxylic acids. And you can see here that we have esters where we have two aliphatic groups, where we have two aromatic groups, and then over here we have an aromatic group and an aliphatic group. But either way, those are all esters. Okay, so we're going to talk a lot about carboxylic acids, and we're going to talk quite a bit about esters in this chapter. So hold on to your hats. Okay, so let's get started by talking about the structure of carboxylic acids. It says here that carboxylic acid groups consist of two very polar functional groups. Okay, so the carboxyl group is made up of a carbonyl. We have a carbonyl here, and we also have a hydroxyl. And so why are those two groups polar? Well, I'm sure you already know by now, but in case you've forgotten, if we draw out the carboxyl group like this, right, you can see there's several dipoles here, right? There's a dipole between the carbon and the oxygen because oxygen is more electronegative than carbon. There's a dipole between the carbon and the oxygen here, right? The singly bound oxygen like that. And there's also a dipole between the oxygen and the hydrogen. And what's the net effect is that you can see is that there's a dipole on the hydroxyl, and there's also a dipole on the carbonyl. So we have two very polar functional groups, and thus carboxylic acids are going to be very polar. So even more polar than an alcohol. And you could jot that in here. More polar than in alcohol. Okay, because up until now, I think the most polar functional group that we've looked at has been an alcohol, but a carboxylic acid can surpass that in terms of polarity. Here are some ball and stick models here. You can see we have the oxygens highlighted in red, we have the carbons in black, and then we have all the hydrogens in gray. So we have a carboxylic acid, and then we have an ester. Anyhow, nothing more there than just some functional groups. Okay, let's talk about the physical properties. I don't know why this slide did this, but it's missing a couple of carbonyls here, isn't it? Anyhow, I'll complete the structure of my carboxylic acids. They look like alcohols, didn't it? Anyhow, so low molar mass carboxylic acids have sharp, sour taste. For example, the carboxylic acid that produces the sharp taste in vinegar is acetic acid, and we've looked at acetic acid already, and we're going to look at it even more in this chapter. But this is acetic acid. That's the common name. The IUPAC name would be ethanoic acid, and you're probably aware that they have unpleasant aromas. For example, if you have 1, 2, 3, 4 carbons like this, okay, this is butyric acid, and not to be anyhow, if you've ever smelled vomit, so when a person vomits, the sharp smell that you smell in vomit is butyric acid. Anyhow, so you're fully aware. Also, the acids that are found in like Granny Smith apples, those are carboxylic acids that give it the tart taste. The tang in Swiss cheese comes from carboxylic acids. Anyhow, it's enough about that. But those are low molar mass carboxylic acids. What about high molar mass carboxylic acids? I bet you if you studied biology, you've probably heard of fatty acids. And fatty acids are important in biochemistry. And before you start to think, oh no, fatty acid, that sounds like something really complicated. All a fatty acid is nothing more than a regular old carboxylic acid, but it will have a long hydrophobic tail on the end, okay? And I just chose an arbitrary number of carbons. That's all the fatty acid is, nothing more than that. So it's just a carboxylic acid with a long tail on it, okay? Long hydrocarbon tail. Anyhow, let's get back to those low molar mass carboxylic acids. And it says here that low molar mass carboxylic acids are water soluble due to hydrogen bonding, water, and with each other. Now, the hydrogen bonding between two carboxylic acids is shown right here. Okay, they're showing the hydrogen bonding between two carboxylic acids. You see, you have the delta plus on the hydrogen, and we have the delta minus on this oxygen, and we're showing a hydrogen bond. And if you're wondering, hey, Mr. Dion, could you draw a hydrogen bond here between the lone pair on the carbonyl and this hydrogen here? Sure, you could draw that. Absolutely, that would count. But what's interesting is that not only can low molar mass carboxylic acids hydrogen bond with each other, they can hydrogen bond with water, right? And if we were to draw a water molecule in here, hey, no reason why we couldn't have hydrogen bonding between this lone pair and the hydrogen on water, because it's delta plus, right? Delta minus, delta plus, like that. Okay. All right. There we go. Give me a thumbs up if you just follow me on physical properties. Like, yeah, I get it. Polar, yeah. Hydrogen bonding, yes. These are all things I've seen before. Good. All right, perfect. Awesome. All right, just looking at physical properties. Before we move on, I just want to show you one more kind of cool thing that's shown here in this ball and stick diagram right here. This is something very unique to carboxylic acids. If you draw a carboxylic acid like this, okay, and draw another carboxylic acid like this, you can see that two carboxylic acids that are identical, what they can do is they can hydrogen bond with each other like this, okay? You can have a hydrogen bond like that, and it kind of makes this, kind of 8-membered ring here. Anyhow, and that's what's being shown right here. And that is very unique to carboxylic acids. And that's one of the reasons why carboxylic acids have such high boiling points. And it's because of this excessive and very strong intermolecular forces here. There's a lot of hydrogen bonding shown right here. So we have hydrogen bonding like that. All right, let's talk about boiling points. It says here, due to carboxylic acids forming intermolecular hydrogen bonds, which is the strongest type of intermolecular force, hydrogen bonds, the boiling points are at higher temperatures than those of any other functional group that we studied. If you take a look at all of these molecules, they all have a molar mass somewhere between 58 and 60. And if we look at the first one, we have butane, which is an alkane. We have methoxyethane, which is an ether. 1-propanol, which is an alcohol. We have an aldehyde and a ketone, propanone and propanal. And then we have the carboxylic acid. And if you look at all these, if we forgot about the carboxylic acid, of course, the one of these that's going to have the highest boiling point would be the alcohol, right, at 97 degrees Celsius. But look, the carboxylic acid even beats that, okay? Beats it by 20 degrees, a little bit over 20 degrees, as a matter of fact, okay? Let's just review the rest of them. The compound that's going to have the lowest boiling point, of course, will be the alkane, because it only experiences London forces. The other compounds, the ether and the 2 carbonyl compounds, well, we went over this before, but an ether will have a lower boiling point than an aldehyde or a ketone, because the dipole is kind of buried by these, or flanked by these 2 R groups a little bit. And then an aldehyde or a ketone, I wouldn't ask you to pick one of those over the other, as long as you knew where the aldehyde and the ketone fall with respect to all of these other compounds, the alkane, the ether, the alcohol, the carboxylic acid. I would be perfectly satisfied with that. All right, there we go. All right, so let's talk about nomenclature. We've already looked at the names of a few carboxylic acids. Just remember that when you have 2 carbons in a hydrocarbon, right, this is ethane like this. And if we have 2 carbons in a carboxylic acid, we drop the E on the end and we replace it with oic acid. So we drop that and it becomes ethanoic acid. All right, like that. Now, ethanoic acid is the IUPAC name. The common name of this compound is acetic acid. And you're going to have that memorized. It's going to come up quite a bit. So let's rehash here on this slide. It says we start off and we find the parent compound. I don't know why it says 4 compounds. Oh, I guess there's an example that was supposed to be on here. Let's imagine the compound, okay? So it's a carboxylic acid that's got 4 carbons, okay? Like this, 1, 2, 3, 4, like that. Bromine here. And so this is the compound they're talking about. So first we find the longest carbon chain. It's got 4 carbons. We're going to start numbering here on the carboxyl. 1, 2, 3, 4. If we have a 4-carbon hydrocarbon, right? 1, 2, 3, 4. That is butane. Butane. So what we do is we drop the E on the end and we replace it with oic acid. So this becomes butanoic acid, like that. And then we number and name the substituents. And we have a bromine on carbon 3. And so this would be 3-bromo-butanoic acid. All right, 3-bromo-butanoic acid. I could even bring that over a little bit like that. Tidy it up. There we go. So 3-bromo-butanoic acid. So that's how we name a carboxylic acid. Here are some examples of carboxylic acids. I've already shown you one of them, which is ethanoic acid or acetic acid. That's shown right here. If I were to have 3 carbons, right? If I were to have 3 carbons, I would have 1, 2, 3. Come on, pen. What's going on? 1, 2, 3. So I'd count off like this. If I had a 3-carbon hydrocarbon, that would be propane, right? That would be propane. So this would be propanoic acid. And you can see that right here. We have propanoic acid. We have a hydroxyl group on carbon 2. And so when we have a hydroxyl as a substituent, we call it a hydroxy. So this is 2-hydroxypropanoic acid. Now you see this name that's below it, which is alpha hydroxypropionic acid. We're going to get into that in a second, but that is the common name. So acetic acid is a common name. Alpha hydroxypropionic acid, that's a common name. Let's look at the next example. If we had a 4-carbon, we already talked about this, it would be butanoic acid. So we have 4 carbons here. So butanoic acid, we have a methyl group at carbon 3. So that's 3-methyl. Butanoic acid, again, the common name is shown at the bottom, which is beta-methyl. Butyric acid, we're going to look at how to name that. It also said on the last slide that if you have 2 carboxyl groups, like is shown right here, we call that a dioic acid. So we name it a dioic acid. And since the longest carbon chain in this molecule has 6 carbons, it's hexane, and we add dioic acid on the end. And this one has a common name, which is adipic acid. And the next one is propane dioic acid, and it has a common name, which is malonic acid. So if you're like, is there a lot more common nomenclature in this? Well, no more than there were with aldehydes. Okay, if you memorized formaldehyde, acetaldehyde, propionaldehyde, butyraldehyde, valeraldehyde, you won't have very much trouble memorizing the common names of the first 5 carboxylic acids. So the common names, we're going to look at these in a second, but let me just show you this slide here. We use Latin or Greek prefixes, and we replace E with ic acid, okay? But those prefixes are like form, right? Acete, propion, butyr, and valor that you already learned in the aldehydes. And so for a suffix, you put ic acid. So we would have formic acid, acetic acid, propionic acid, butyric acid, and valeric acid. And also, instead of using numbers, right, normally when we're using IUPAC nomenclature, we would number our carboxylic acid like this, or we would put, 1 on the carboxyl, 2, 3, right, so on and so forth. But when we're using common names, we don't do that. We use Greek letters, and the first letter comes on the carbon after the carbonyl carbon. And so we have alpha, beta, gamma, and delta. And so let's look at these examples here. We have a 4-carbon Carboxylic acid, we want to give it a common name, so it would be butyric acid. And then we have the hydroxyl here, and so that would be alpha, and then it's on beta, so it's beta hydroxybutyric acid. Here we have a 3-carbon carboxylic acid, or that's the longest carbon chain, so it's propionic acid. And we have the hydroxyl group here, and so it's alpha hydroxypropionic acid. All right. And if you're wondering, do you have a table of these, Mr. Dion? Absolutely, I do. It's right here. This is table 14.1 from our book. And the carboxylic acids that you have to know the names of, the ones you have to have memorized are these ones right here. Formic acid. So formic acid, acetic acid, propionic acid, butyric acid, and valeric acid, right? Formic acid has 1 carbon. Maybe I should just put 1 carbon. Then we have 2 carbons in acetic, 3 carbons in propionic, 4 carbons in butyric, 5 carbons in valeric. And if you want to know the IUPAC names, they're all shown right here. So methanoic, ethanoic, propanoic, butanoic, and pentanoic acid. Again, you have to know all of these. Formic acid gets its name from, in French, ant is fourmi. So, you know, it's Latin, something close to ants. And ants, their defense spray contains formic acid. Some ants have a defense spray that they can use against predators. Acetic acid is found in vinegar. I told you that earlier on. I told you that propionic acid is what gives Swiss cheese its tang. I told you that butyric acid was the acid that's found in vomit. It's also found in rancid butter. I guess that might be even a better example. In valerian root, that is where we would find valeric acid. Anyhow, you see these other acids down here. You don't have to memorize these. Caproic acid, capric acid, palmitic acid, and stearic acid. But I'll put this bug in your ear that later on, when we start talking about fatty acids, you will hear me talk about stearic acid. And you can see that stearic acid comes from a steer, right? It comes from beef fat or tallow, all right? And so that's a fatty acid, again, that we will look at. It's got a total of 18 carbons in it. Anyhow, something kind of fun to look forward to there. All right, let's look at some benzoic acid derivatives. We've already looked at benzoic acid earlier on in this class. I asked you to memorize the name and the structure of benzoic acid. You can shorten that to, you know, benzoic acid, if you just want to write P, CO2, H like that, that's the same thing as benzoic acid, right? Because we use pH to represent phenyl. And so that's benzoic acid. If you have a carboxyl group on a toluene, so you see that we have a toluene here, we call that a toluic acid. And of course, since the carboxyl is meta to the methyl group, then it's metatoluic acid. So you can imagine what the structures of ortho and paratoluic acid are. Next one here, we have orthobromo benzoic acid. If you were to have, you know, let's say you put a, you know, chloro group here, and you had your carboxyl. Could somebody give that compound a name? Not a trick question. What would the name of this compound be? Anybody have a name for this guy? Yeah, it would be metachlorobenzoic acid. Exactly. So what Johnny said, he says it would be metachlorobenzoic acid. Absolutely. Okay. And I maybe could have picked a better example because we have meta-iodobenzoic acid right here. What else? The diaromatic acids like phthalic acid, you don't have to have that memorized. There's phthalic acid and isophthalic acid. All right, there we go. So those are some benzoic acid derivatives. Carboxylic acid with a phenyl substituent. A phenyl group is benzene with 1 hydrogen removed. And so we've actually already looked at the phenyl substituent, right? I told you that, you know, if you have a benzene ring as a substituent, okay, not as a parent, like that, we abbreviate that pH like this. So phenyl, not to be confused with the measure of, you know, the concentration of hydrogens or protons, which is pH like this. That's something completely different. That's another day. Anyhow, so if we had acetic acid, right? So if we had acetic acid, it would be CH3 with the carboxyl group over here. So that would be acetic acid, or you could call that ethanoic acid, either way. And so if we have a phenyl group on there, we would call it 1, 2. So this would be 2-phenyl ethanoic acid. If we want to give it the common name, of course, this is the alpha position, like that. So it would be alpha phenylacetic acid. Same thing applies here. We have propanoic acid. If we have a phenyl group at carbon 1, 2, 3, that would be 3-phenyl propanoic acid. Or if you want to give it the common name, we have alpha and we have beta here. It would be beta phenylpropionic acid. All right, so a lot of nomenclature here. Now let's move on to common dicarboxylic acids. My students come up with all kinds of silly stuff that they've, little acronyms and little things that they've shown me to memorize different things. And of course, if you want to have a dicarboxylic acid, you've got to have at least 2 carbons, okay? So the simplest dicarboxylic acid is oxalic acid. It's got 2 carbons. When you have 3 carbons, that's malonic acid. 4 carbons is succinic acid. 4 carbons. 5 is glutaric acid. And 6 carbons is adipic acid. So if you look at the first letters, it's O, M, S, G, A. I don't know what this means, but my students came up with this mnemonic, which is oh my stars go away. I have no idea why they came up with that, but anyhow, it's just always stuck. I never forgot it when my students told me that my first semester teaching in Colorado. And I always thought it was funny. So, oh, my stars go away. Maybe there was somebody they didn't like in the class. I don't know, but anyhow, that's the way I've always taught students to memorize it since I've moved here. So oxalic, malonic, succinic, glutaric, and adipic acid. And you should have these memorized. But again, if you can come up with that mnemonic, and you know that oxalic acid has 2 carbons, you'll be in good shape. You'll be able to remember that pretty easily. Okay, there we go. Give me a thumbs up if you just follow me on nomenclature of carboxylic acids. Nothing more than just nomenclature. Yeah, all right, cool. All right, 2 people, I'll take it. Let's try a couple of examples here. I'll put some carboxylic acids right here and see if you can name them. So if we had, we'll try 3 different compounds here. But first we'll try this. We'll try this. And we're going to go for IUPAC names to begin with. Do this. All right, let's see if we can name these. I'm just going to go upstairs for 1 second. All right, if anybody wants to put forth a name for any of these, go ahead. Anybody has a name for any of these? All right, so William has a name for the second one, which is 2,4-dimethyl pentanoic acid. I would buy that. Yeah, we have 1, 2, 3, 4, 5 carbons. So it must be some kind of pentanoic acid. And we have a methyl group at carbon 2 and carbon 4. So yes, William, I would say that's 100% correct. You got 2,4 dimethyl pentanoic acid, like that. What else? 3-bromo 4-fluorobenzoic acid. Okay, let's try that one. So here's our parent, which is benzoic acid. The number 1 is going to go on the carbon that has the carboxyl group. So I have 1, 2, 3, 4. So yeah, I've got 3-bromo because bromo comes before fluoro alphabetically. 3-bromo 4-fluoro benzoic acid. That looks good. All right, what about the, and somebody put 6,6-difluoroheptanoic acid, Johnny. Let's see here. We got 1, 2, 3, 4, 5, 6, 7. Yeah, so if we have a 7-carbon hydrocarbon, right, that would be heptane. We scratch off the E, it becomes heptanoic acid. And we've got 2 fluorines on carbon 6. And so that would be 6,6-difluoroheptanoic acid, like that. All righty. There we go. So that's a little practice with carboxylic acid nomenclature. Let's talk about some important carboxylic acids. It says here that more complex carboxylic acids are found in a variety of foods. Citric acid, for example, is found in citrus fruits like lemons and limes and oranges. And so citric acid is a carboxylic acid. It also says that bacteria in, I don't know, this is bacteria in mild. It should be bacteria in milk. So we'll pronounce that in. So bacteria in milk, there we go, produce lactic acid as a product of the fermentation of sugars. So lactic acid is a carboxylic acid. If you've ever done strenuous exercise, when you get sore, that's due to a buildup of lactic acid in your muscles. Next is tartaric acid, which is found in baking powder. It's a carboxylic acid. As I told you, green apples or Granny Smith apples, malic acid is found in those, which is a carboxylic acid. So tartaric, what else? Lactic, citric acid. And then fatty acids are nothing more than long-chain carboxylic acids that are found in all kinds of plants and animal sources. So, for example, we just talked about beef fat, which is tallow, or any kind of thing like bacon fat or vegetable oil. We're talking about fatty acids there. All right, some important carboxylic acid. Here are the structures of some of those carboxylic acids. Malic acid, you can see that we've got the 2 carboxyl groups, and we've also got a hydroxyl group. Tartaric acid is pretty closely related to malic acid. It just has 1 extra hydroxyl group. Lactic acid has a very simple structure. It's only got 3 carbons and 1 hydroxyl group. And then you see here the citric acid has got quite a big structure here. Anyhow, so you don't have to have any of those memorized. That was more of just an FYI, just so you're aware that there are many carboxylic acids found in the foods that we eat day to day. All right, are you ready? Strap on your skates, Gordy. We're going in. We're getting into the fun stuff. The reactions of carboxylic acid. So this is where it gets a little bit more involved. And so make sure you try to follow along with me on these. And the first reaction we're going to look at is the preparation of a carboxylic acid from a primary alcohol or an aldehyde. And the good news is, if you're looking at this, you know what's in this green box here and saying, hey, I think I saw that somewhere before. Well, you'd be absolutely right, because we talked about this in the aldehydes and ketones chapter. We said if you take a primary alcohol, right, and you oxidize it using either chromic acid or potassium permanganate, you can produce an aldehyde. But it also told you that it's really difficult to get it to stop at the aldehyde, and usually it will just keep going and oxidize further to give you a carboxylic acid. Okay, and that's shown right here. And how do we know that this is oxidation? Why? Because what? We're gaining oxygen, right? We're gaining one oxygen atom when we go from the aldehyde to the carboxylic acid, like that. Now, what about carboxylate anion formation? Well, remember, a carboxylic acid is an acid. It's not a strong acid, but it is an acid, okay? And we could even put that in here. We'll say carboxylic acids are weak acids, okay? But why are they considered acids? Well, what's an acid? An acid is a proton donor. And it says here, when a carboxylic acid is dissolved in water, it's going to deprotonate to form a carboxylate ion and a hydronium ion. Okay? It says here that carboxylic acids are weak acids with dissociations of less than 5%. So let's go over this in a little bit more detail here. I'll just bring this down a little bit. Let's think about a strong acid. I want somebody to name me a strong acid. Give me your favorite strong acid. Give me the strongest acid you got. Good one. Sulfuric acid. I'll take that to the bank, right? Sulfuric acid is a really strong acid. Well, when you put sulfuric acid in water, you put sulfuric acid, H2SO4. If you put that in water, okay, we draw the arrow in one direction. Right? The arrow is going in one direction because this is a strong acid, and so we're going to get complete dissociation. And what's going to happen? The acid, sulfuric acid, is going to donate H+. Where is that H+ going to go? It's going to go onto the water molecule to produce hydronium, okay, a hydronium ion, plus we're going to end up with HSO4 minus, right? What's left over? So we end up with hydronium and hydrogen sulfate, like that, okay? Now, if we take a carboxylic acid, let's take acetic acid. So it could be any carboxylic acid, but we'll just choose acetic acid. So there's acetic acid. When we do the same thing, when we put that in water, since acetic acid is a weak acid, right, as are all carboxylic acids, we only get partial dissociation, right? We don't draw an arrow in one direction, we draw the arrow going back and forth because it means partial dissociation. But we're still going to get the acid donating this proton to the water to give us hydronium, and we're going to end up with the carboxylate, okay? And the carboxylate in this case would be called acetate, okay? So this is your carboxylate, okay? Think about things that end in ate in chemistry: sulfate, nitrate, chlorate, perchlorate. Okay? Carbonate means it has a negative charge. We have a carboxylate like that, okay? There we have it. Give me a thumbs up if you follow me on strong acid versus weak acid, and that a carboxylic acid is a weak acid. Very important. Very, very important. Great. Okay, good. Very important concept moving forward in this class. Okay? You know, sometimes people on the street, you know, they hear the word carboxylic acid and they're like, oh no, is that scary? And you're like, well, you put it on, you know, if you've ever used salad dressing, you've messed around with you've eaten carboxylic acid. If you've ever had an apple or an orange, right? You've eaten carboxylic acids. If you've ever had yogurt, you've eaten a carboxylic acid. So nothing to fear there, all right? Well, let's talk about neutralization reactions. It says here that carboxylic acids do react with strong bases to form carboxylate salts in a process called neutralization. The acid protons are removed by the hydroxide to form water and a carboxylate, and the equilibrium shifts to the right with the removal of a hydrogen. Let's back up here and go back all the way back to Chemistry 101 and do a little review here for a second. If you take a strong acid, I'm going to choose hydrochloric acid, okay? If you take hydrochloric acid, okay, which is a very strong acid, and you react it with sodium hydroxide, which is a strong base, okay? So strong base and strong acid. What's going to happen? Well, as it said in the slide, you're going to end up with a salt, which is sodium chloride. Okay, that's table salt, but it's also a salt, and we'll put here like that. Plus, you're going to end up with water. Okay, so end up with a salt plus water, like that. Okay, I'll write that in here. This is a salt, and how do we know it's a salt? Because it's comprised of an anion and a cation. The cation comes from a metal. The anion comes from a nonmetal and water. Well, look what happens here. When we take a carboxylic acid and we put it in a strong base, you end up removing this proton, and it's going to combine with the hydroxide to give you H2O. Then what are you left over? You're left over with the negative charge on your carboxylate, okay? But it's going to interact with the cation to make a salt. So we call this, oops, do that. We call this, this is a carboxylate, and if I have it interacting with a cation like this, then we call it a carboxylic acid salt, right? Why is it a salt, and why is the other one not a salt? Because it's got the cation. Okay. All right. And so, give me a thumbs up if you follow me that far. Not done talking about it, of course, but I just want to know that you're with me that far. Good. Okay, great. All right. Well then, let me show you how this actually works. Now, I'm never going to ask you to draw anything like this, but I just want you to see this. You're old enough, okay? You're old enough to see this. I'm going to show you that in reality, okay, if I draw my carboxylic acid, okay, and I'm going to draw the oxygen-hydrogen bond explicitly. I'm going to draw the positive charge on my sodium and the negative charge on my hydroxide, like that. Okay. What's really happening, if we back up here, it says right here, watch carefully, the acid protons are removed by the hydroxyl. Okay. So what actually happens in real life, and again, you don't have to draw this. This is just to explain it. The negative charge on that oxygen on the hydroxide is actually going to go and grab that hydrogen. And there's already 2 lone pairs on this oxygen. And then you're going to take this pair of electrons and put them on the oxygen like that. Okay? And that is, again, going to leave you left over with your carboxylate. Okay? So it's going to have a negative charge. It's going to be balanced out by the positive charge from the sodium, and then you're left over with H2O. And where did that come from? It came from H2O, like that. Okay? OH plus H gives you H2O, all right? There we go. So neutralization. So not only can you neutralize strong acids, and again, you would have seen that in general chemistry, but you can also neutralize weak acids like carboxylic acids. Okay, here we go. So this slide just shows or exemplifies some acid-base reactions, and it's just trying to color code it here to help walk you through it so you can see what is actually going on here, right? And these are just 2 specific examples. If you take ethanoic or acetic acid, which means the same thing, the acidic proton, maybe I should have told you that, or maybe I should have highlighted that for you, that when you look at a carboxylic acid, any carboxylic acid, this proton right here, this is the acidic proton, Okay, so that's the one the carboxylic acid is going to lose, and that's why it's highlighted in red here, okay, for both of the examples. Anyhow, so again, that hydrogen is going to combine with the hydroxide to give you water, and then you're going to be left over with your carboxylate. Similarly, you're to do the same thing with benzoic acid. Sodium hydroxide is going to react with that, or the hydroxide will react with the proton to make water, and you're left over with the salt, okay, the carboxylate salt. All right, there we go. Let's talk about how we would name those salts, right? We've looked at quite a few salts already, and if you followed me on the nomenclature of carboxylic acids, which I'm sure most of you did, Naming a carboxylic acid salt isn't all that difficult, and I'll put a little bug in your ear here for later on in this class, is that you're going to be able to use this to help you name esters too. Okay, so esters, because later on we're going to learn how to name esters, and the nomenclature of esters is very similar to the nomenclature of salts of carboxylic acid. So here's what we do. First we add the cation's name. So if we go back to these examples here, you can see the cation in both cases is sodium, and so what did they put first? They put sodium and sodium. Okay, so that's, and you're like, well, if it's lithium, would I put lithium? Yes. If it's potassium, could I put potassium? Yes. Okay. So first step's not too bad. Okay, you just name the cation, and then you drop oleic acid and you add 8. And so for this example that is in this slide, if you had this carboxylate salt, right, you would have sodium, and then this is the carboxylate of benzoic acid, and so it would be benzoate, right? We drop oleic acid, we get benzoate, and so that would become sodium benzoate, and so that's what this is right here, is sodium benzoate. Where would you find a use for the salt of a carboxylic acid? Well, the salts of fatty acids, which are carboxylic acids, are found in soaps. So bar soap or some hand soaps they're liquid, preservatives, antifungal medicines, and also used to control the food pH of certain foods. I'm not going to ask you a whole lot about that, but you should know that a soap is the salt of a carboxylic acid. And if you're wondering, will we talk about that more? Oh yeah, we're going to talk about that a lot more. Give me a thumbs up if you feel like you're part of the way with me on carboxylic acids, because now we're going to switch gears and talk about esters. Are there any questions about carboxylic acid? Any burning questions that I didn't answer, or something, you know, some stone that's left unturned? Okay. If not, remember, I don't expect you to learn everything just by hearing the sound of my voice, and I don't expect you to know it all in, an hour. That's impossible. Okay, you're going to have to go back, try the practice problems that I've assigned, take a good look at them, try to memorize the different reactions. All right, well, let's switch gears now and let's talk about esterification. Would you guys like to take a quick break? I've been going on for quite a while. Okay. All right, why don't we take an 8-minute break? I'm going to stop here. I need a drink of water. Stop.